For this first part of the lecture series, we would be learning about some of the basic concepts. The series has been planned to start with why should we learn reaction mechanism and what is the role of bond breaking and bond making during the course of organic reactions, and what is the significance of arrow notation in reaction mechanism. Then finally, we would deal with some of the reagents which participate during organic reactions and what is their role in the organic reactions. So, we start with why should we learn reaction mechanism? Generally, what is the notion about organic chemistry? We know that most of the students feel that organic chemistry is just mugging up the reactions. There is a whole plethora of reactions which need to be crammed and just written for your examination. But what is the reason of this kind of a notion? Actually, the reason in most of the cases that we don't understand the reaction in the manner they should be. Then what is the way out to deal with this problem or to do away with this notion? Well, we should know the exact mechanism of the organic reactions by which we would get interested in knowing more and more. We can say, to the extent that reaction mechanism is in fact a tool which helps to organize the organic reactions into various types, as we shall see later. And it also tells how exactly what are the various steps which are taking place in organic reaction, and it relates the different reactions which generally look unrelated. There may be two reactions which may be leading to very different products, but then by ways of reaction mechanism we come to know of a common link between the two reactions, that is, the intermediates which from one step to the other lead finally to the products. And also during the course of organic reactions, how are the substituents affecting the speed or the rate of the reaction and the amount of the product formed is also studied by virtue of studying the reaction mechanism. And not only that, we come to know of a number of new reactions which take place every day and the new researches which are done by ways of studying organic reaction mechanism. So, the reaction mechanism not only helps us to know what is existing and why is it existing, but also it guides us in a way that one can do some improvement in the existing reactions. Well, suppose we take an organic reaction like an alkyl halide reacting with sodium hydroxide to give an alcohol and sodium bromide. Similarly, an alcohol reacting with PCl5 and giving an alkyl halide. These are the examples of organic reactions which you may be familiar with, but how do we ascertain that this reaction is taking place and how is it actually happening? We take this example to know what exactly is happening. We take an alkyl halide RCH2Br and treat it with sodium hydroxide, which gives us an alcohol and sodium bromide, as we saw in the previous slide. So, what is happening? Can appreciate that bromine from alkyl halide is getting replaced by the hydroxy of sodium hydroxide and giving us alcohol, and of course sodium bromide is getting eliminated. What exactly is happening here? We can see that there is this CH2Br bond which is breaking. As a result, this bromine is getting eliminated and getting attached to the sodium of sodium hydroxide. In turn, what is the other thing happening? We are getting the formation of a new bond between the carbon of alkyl halide and hydroxy, which has come from the sodium hydroxide reagent. So, what is happening in this reaction is that besides a bond breaking, there is a bond making. We can say that organic reactions involve bond breaking and bond making. So, we have to see bond making is not a problem, but then we have to see how is the bond breaking taking place. What are the ways in which the bond breaks? There are generally two ways of bond breaking. One is heterolysis. What is heterolysis? The bond breaks in such a manner that one fragment takes away both electrons of the bond, leaving the other fragment with an empty orbital. See, heterolysis means, heterolysis is made up of two words. Hetero is different, lysis is cleavage or breaking, which means that the breaking is taking place in such a manner that the bond breaks in a heterolytic manner. What does that mean? It means, suppose we have a molecule with two atoms in it, A and B. Both of these in a covalent bond are sharing an electron each. As you can see here, the bond breaking is in a heterolytic fashion. That is, the bond is breaking in such a manner that both the electrons which were once shared by A and B both get on to only the A atom. What happens as a result of this heterolysis is that A gets the shared pair of electron and gets a negative charge on itself, whereas because the B atom does not have that shared electron with it or the shared pair, so it is left with a positive charge. Now you think of a vice versa situation wherein the heterolysis is taking place in such a manner that A is getting nothing and B gets the shared pair of electron. What will happen in this case is that B will become negative by virtue of getting the shared pair of electron, where A will remain deficient of that electron. This can be depicted in a different manner, like reaction between A and B, wherein this particular pair moves on to B and what we are getting is A plus and B minus, which this A plus and B minus as a result of heterolytic bond cleavage lead to ions. So, we can say that heterolytic bond breaking or heterolytic bond cleavage produces charged fragments or ions, and such reactions are called ionic reactions because they produce ions. For heterolysis to take place, the bond should be polarized. What does that mean? It means that the two atoms which are constituting this particular bond should have some difference in electronegativity, because then only one of the atoms will attract the shared pair of electron, whereas the other one will be able to let this pair go to the other atom and form the ions. And heterolysis requires separation of opposite charges, therefore requires more energy. This is very well understood, as we know that the two atoms with different electronegativities were bonded together because of the covalent bond, and breaking this covalent bond will definitely require more energy. But why does this reaction then take place? The reaction takes place because there is a driving force also. What is the driving force? And that is the formation of a new bond during the course of this reaction, which provides energy enough to cross the barrier of activation energy and lead to the formation of the product. And the heterolysis is generally facilitated by another species with unshared pair of electrons, so that that pair can be given to the one which does not, which is deficient in that particular electron, and give rise to the product. The other way of bond breaking is homolysis. Homolysis is the type of bond breaking which takes place in such a manner that each of the fragment in the molecule gets an electron each. And the homolysis word is also made up of two words, homo and lysis. Homo means same and lysis is cleavage or breaking, similar to the heterolysis. And here what exactly happens is, if we have two atoms in the molecule and which are sharing an electron each, the bond breaking takes place in such a manner that both the fragments get an electron each. So this can be depicted in this manner also with the help of arrows, and we get two moieties which have an electron each as a result of homolytic cleavage, and such moieties are called as radicals, which in fact form very important intermediates in organic reaction chemistry. Therefore, homolysis gives rise to radicals which are with an unpaired electron. The ways of bond breaking can be depicted in this manner also. It makes you learn it better that heterolysis is giving rise to two ions and homolysis is giving rise to two radicals as shown in this particular graphics. There is yet another way by which bond making and bond breaking takes place, and we call it as simultaneous bond making and bond breaking. So what exactly happens here is, as the bond breaks, the other bond gets made also. It happens in most of the photochemical reactions, and which we call as pericyclic reactions. As you can see here, that we have butadiene and butene, wherein, as the arrows are showing, the bond between these two gets formed. This bond in turn gets shifted to the single bond, and a bond from the butene molecule gets shifted in between the butadiene and butene molecule. As a result, we get formation of substituted cyclohexene. So these types of reactions are called as pericyclic reactions, wherein we have simultaneous bond breaking and bond making. Now you have seen that the way in the previous reaction also and in this reaction also, there is a way by which we show movement of bond or movement of electrons while depicting the reactions, while depicting the reaction mechanism in organic reactions. So it becomes very important to learn that what do these arrow notations mean to us and how are they significant while we study reaction mechanism. That is what we call as arrow notation, and there the maximum significance is of the curved arrows. The arrow notation generally tells the direction of flow of electrons in a reaction and also shows how a starting material is getting converted into the products. The two types of curved arrows which we generally use in depicting the reaction mechanism is the curved arrow which has a head. The curved arrow with a double head indicates the displacement of a pair of electrons. You can see here in this general example wherein we showed heterolytic cleavage and the shared pair of electrons moves to the A. Now the direction of the head is towards the atom which is electron deficient or which has the tendency to attract this particular electron pair. As a result, it gets a negative charge. Then we have a depiction with curved half arrow which shows displacement of a single electron. So, what we saw in the case of homolytic fission is actually by the depiction of curved half arrow which shows each electron is shown to be moving to the respective atoms which are leading to the formation of radicals. This is how the curved half arrow is used. There are some general features of curved arrows which can be listed in a manner that these show the direction of electron flow in a reaction mechanism as we saw, and generally these point from the source of an electron pair to the atom receiving the pair. Also, they show the movement of single electrons wherein we saw the use of half curved arrow. And these are generally showing the flow of electrons from a site of higher electron density to a site of lower electron density. But they never show the movement of atoms. As you would see when we are doing more and more organic reactions, that the atom is never shown to be moving with the curved arrow. It is only the flow of electrons, as in this example, wherein this electron pair from oxygen is moving to this proton, and in turn, in fact, it is taking away this proton and giving rise to a positive species H3O plus and Cl minus. So, this is the way we use curved arrows. Well, there are a number of ways by which curved arrows can be used in various types of reactions. What are these types? In one of the type of reactions, it shows the dissociation of a polar covalent bond into its ions. When in a molecule which we saw in the case of heterolytic fission, B is more electronegative than A, in that case the arrow will depict the movement of this pair to B and lead to the formation of ions. So, movement of an electron pair converts the A-B covalent bond into the lone pair on atom B. Then we have another type of depiction wherein formation of a polar covalent bond from ions. So, if you have two charged species reacting with each other, A plus and B minus, the lone pair from B moves towards the atom A or the species A and leads to the formation of a bond between A and B. So, a lone pair on B moves towards A, becoming a new covalent bond between them. Yet in another way of curved arrow depiction, we have simultaneous formation and dissociation of two covalent bonds, what we saw in the case of pericyclic reactions also. So, A and B if are polarized and we have another charged species, then this will donate the electrons to the species which is electron deficient and form a bond with that particular species or atom and give the other one as another ion. So, movement of two electron pairs results in substitution of one bond for the other. Then we have addition of an electron pair donator or an electron pair acceptor to a multiple bond. You know that multiple bonds have the ability to get saturated during the course of a reaction by ways of accepting an electron pair or a charged species which can donate an electron pair to the one which is electron deficient and lead to the formation of a saturated compound, as is shown here. In one case that is depicted as A, we have an electron pair donor as one of the species which is giving to of course the one which is electron deficient, while in this particular case we have this double bond which is electron rich, which is giving electrons to a positively charged species and thus leading to the formation of a bond and the product in these particular reactions. There are a few other arrows which are used while we are depicting reaction mechanism of organic reactions. We have arrowhead made in between in a line which depicts inductive effect. So, the inductive effect basically depicts the induction of polarity in a bond, and we have double headed arrow which has heads on both the sides, and it depicts the resonating structures. Resonance is the delocalization of pi electrons, as you must have seen in the case of benzene and many other conjugated alkenes or the unsaturated compounds which are stabilized due to the presence of resonance. This also, while explaining the stability of a number of molecules, will come across a number of times. Now, this half-headed arrow in both the sides depicts equilibrium, that is, that the reactants and the products remain in equal amounts in this case. And whereas two arrows in opposite direction with double head denotes a reversible reaction. The reaction is proceeding in both the directions, in the forward as well as in the backward direction. Then we come to the explanation of all those species which are very crucial for an organic reaction to move. We call these as the reagents. Reagents are the species which react with substrates to form a bond to a carbon atom. The reagents generally used in organic reactions are of two types: nucleophiles, which are also called as Lewis bases, and are the carbanions. Electrophiles are just opposite to the nucleophiles, and they are called as carbocations and also the Lewis acids. Nucleophiles are, as the name depicts, nucleus loving. Because they are nucleus loving, that means they are electron rich. They have high electron density and therefore they seek a positive center other than, of course, proton, especially that of a carbon atom, such as a positively charged carbon atom. Why we say other than a proton is, you would understand later when we are comparing a nucleophile with a base. Therefore, to all nucleophiles we say that they should not be accepting a proton or taking a proton, otherwise they become Lewis bases, but should seek a positive center. And because they are electron rich, so they donate electrons and behave as Lewis bases, but not actually are Lewis bases. As you can see in this particular reaction, a nucleophile is attacking an electrophile. So, nucleophile has an unshared pair of electrons, attacks the positive center of the carbonyl compound, and therefore this particular bond moves to the oxygen, and what we get as product is nucleophile attached to the positive center of the carbonyl compound and forms a bond here. Similarly, if we have an electrophile here, not necessarily a carbonyl compound which has a positive center and an oxygen which is electronegative enough to make it electropositive, but otherwise if we have a positive carbon center, then also the nucleophile will attack the carbon and form the bond. So, nucleophiles can be both charged as well as neutral, and we shall see later which are more stable or which are more reactive, but these are some of the examples for charged and neutral nucleophiles. We have charged chloride, hydroxide, cyanide, the thiol group or the methoxy, and they are equivalent neutral parts. That is, we have an alcohol, water, a thiol, an amine or an ether. So, these are generally the types, but then there are number of other species which can act as nucleophiles. So, the other types of reagents we come across in organic chemistry are called as electrophiles. Electrophiles, as the name suggests, are electron loving. Because they are electron loving, they are electron deficient species that seek electron to achieve a stable noble gas configuration, and they attack an electron rich, or we may say a nucleophilic center. Because they are electron loving, so they are Lewis acids, but will not donate a proton and could be carbocations and accepting an electron pair from a Lewis base. These are sounding little complex, but then all of these terms are interrelated, as we shall see when we are trying to compare a nucleophile with an electrophile, or a nucleophile with a Lewis base, or an electrophile with a Lewis acid, or vice versa. As we can see in this particular reaction, a carbocation which is a Lewis acid and electrophile is attacked by a base, Lewis base, or it could be otherwise a nucleophile also, which is electron rich species, which will attack this positive center and form a bond. So, the electrophiles are electron poor species that are sometimes not carbocations and react with electron rich centers. Such electrophiles wherein we have an example which we saw in the case of nucleophiles are carbonyl compounds. We have a positive center here which acts as an electrophile, electron deficient, and is being attacked by a Lewis base, and during the course of this reaction forms a bond and the product. Similar to the nucleophiles, even for electrophiles we have charged and neutral species. In charged we have a number of examples: nitronium ion, nitride, ammonium, hydronium, and acyl plus bromide, bromonium ion also. They are neutral counterparts, CO2, SO3, BF3, or acyl chloride, aluminium chloride and zinc chloride, which are also are the very known Lewis acids. So far in this particular lecture series, what we saw was why actually we study the reaction mechanism. What is the need of studying, knowing the reaction mechanism of organic reactions, and essentially I hope we have realized that knowing reaction mechanisms make us understand organic reactions very well, and therefore makes them understanding also, and not only that, gives one a chance of improving the existing reactions. Then of course we saw some of the very important depictions in reaction mechanism, that is the arrow notation, and what is the significance, the use, and what do they exactly depict while we are explaining the course of a reaction. And then the most crucial parts of a reaction or of organic reactions is the reagent which is used to accomplish an organic reaction, that is the reagents, about which we saw that generally there are two types of reagents we are coming across. They are nucleophiles and electrophiles, about which in general we have come to know the basics behind these two reagents. The details would come up later.